So this next lecture is on net force. You might remember from the last lecture that we had situations where there was an object not moving, and in that situation, the x and y forces added up to 0. So there would have been a force pushing on the right and another force acting on the left, and those two forces would be equal. You'd also have usually a gravitational force being exactly equal to a normal force acting in the opposite direction. So in that case, we would not have an object moving. Net forces is interesting because it allows us to determine if motion will start to occur. And in those situations, the net force was both 0 in the x direction and 0 in the y direction. So we are going to go in through this, and we'll see how we can use net force to help us understand whether motion will occur. So to start off, it says here, since a single force seldom acts on an object, it is often necessary to find the sum of forces acting on an object. We call that vector sum the net force. Another name for it is the resultant force, and we usually write it as F with subscript net. Here's a little image of an object with it looks like 5 forces acting on it. We can determine if that object is going to move by analyzing all those forces and seeing if the net force is 0 or not. If it's 0, it will not move. If it's not 0, it will move. So net force, it's the vector sum of all forces acting on an object. It's also known as the resultant force. F net is equal to the sum of all the forces, F1 plus F2 plus F3, and so on and so on. So in order to determine the net force acting on an object, we would use a free body diagram sometimes to help us understand the situation. Let's consider a weightlifter who holds a weight over their head by exerting a force of 1.6 kilonewtons up. The force of gravity acting on the weight is 1.6 kilonewtons down. So the free body diagram of the weight and the net force acting on the weight would be as followed. So in this case, on the right you see F net equals Fn plus Fg. Fn is 1.6 kilonewtons up. Fg is 1.6 kilonewtons down. In order to add those, it might be better to switch so that they're both facing the same direction. So it would be 1.6 kilonewtons up minus 1.6 kilonewtons up, and that would get us to 0. So there would be a 0 net force. Okay, here's a question. It says, if the objects shown here in A and B are at rest, what is the missing force? So in our first situation, we have a 12 Newton force acting up and an 8 Newton force acting up. And then we have another force, an Fg, acting down. So let's try to figure out what that is. Let's turn on the camera here. So in my first situation, I'll call this 1A. We have a net force, F net, of 12 plus 8. Those are both acting up, minus Fg. And we know that this F net is 0 because they're saying that that's defined in the question. So we have 0 equals, well, I guess this would be 20 minus Fg. So when we move the Fg to the other side, we have 20. And we set this as down from the start. So now we have to write our answer with a direction, 20 newtons down. And I use an arrow for down. Let's look at our second question. So let's check this out here. We're trying to find the force up and the force to the left. So for the force that's acting up, we don't have to write anything because we know if that's 22 newtons down, then the force acting up would be 22 newtons. So we can write that down. The other one, we have a 15 acting to the left and a 28 acting to the right. So for 1B, I think it says Fn. We can state that that's going to be 22 newtons up. For the others, F net equals 0 it would equal F plus 15, that's the ones acting to the left, minus 28. So the F would be, the 28 would move to that side, and then subtract 15 from it. 28 minus 15 would be 13 newtons acting to the left. Let's look at another problem here. It says the free body diagram for a car at rest on the ground is shown here. Determine F1 and FG. And it says the car is at rest, so that means FG is going to have to be equal to the normal force, the 13,000. F1 would be equal to the sum of the other two forces that are acting to the left. So that would be 1,250 plus 1,400, so it's going to be 2,650. It says, here's an interesting question. It says, how would your answers change if the car was moving at a constant velocity, assuming none of these forces change? Well, it wouldn't. There would be no change here. When something's moving at a constant velocity, it is not accelerating. That means that there is no force acting, no net force acting upon it. Now, earlier we were talking about whether motion will occur. Motion could still occur even if F net equals 0, but it will only occur if there's a constant velocity already acting on the object. So in reality, when we're looking at the force, if there's a net force applied, we know that there's an acceleration happening. And if there's an acceleration happening, we know that motion is occurring. But motion could also be occurring if there is no acceleration. We would just have uniform motion. Okay, here's a problem. It says two children are fighting over a toy. One pulls with a force of 20 newtons to the east. The other pulls with a force of 5 newtons to the west. This is a pretty simple situation. We don't necessarily need to draw the free body diagram or do much to calculate this. 20 newtons east plus 5 newtons west would be the same as 20 newtons east minus 5 newtons west. So that gets us to 15 newtons east. Here's another problem. This one we will work out. It says a trunk is acted upon by forces of 30 newtons north and 40 newtons to the east. So we're asked to draw a free body diagram of this. And then we're asked to also find the net force. So that would be, oops, let's see here. This is question 4 we're working on. So our net force, F net, is equal to 30 north plus 40 east. North and east are cardinal directions that are that have a 90-degree angle between them. We can't add them together. We need to add them using Pythagorean addition. So it's 30 squared plus 40 squared. That gets us to 50. Now we can't solve this here until we find out what the angle is. We don't know what the direction is. So our direction is found by doing the inverse tangent of the 30 over the 40, the lower value over the greater value. And when we do that, we end up with 53. Sorry, I don't think we end up with 53. Let me calculate that, actually. So let's turn our calculator on. We have 30 over 40. That would be 0.75. And if we find the inverse tangent of that, we get 37 degrees. So this is 37 degrees. If I have 50 newtons here, actually I'm just going to write this on a separate line. 50 newtons, I need to write the direction. This goes towards the greater of these directions, so 40 is greater than 30, so it's going towards the east first. 37 degrees north. So east 37 degrees north is our solution for that one. And last one we'll do here, it says a clerk pushes a parcel towards a customer with a force of 7.6 newtons east. The frictional resistance of the parcel is 6.5 newtons west. And both the force of gravity and the normal force have a magnitude of 9.9. Draw a free body diagram of the parcel and determine the net force acting on it. Well, in this case, your free body diagram should have a 7.6 force acting on the east, a 6.5 force acting on the west, a normal force of 9.9 acting up, and a gravitational force acting down at 9.9. Your net force is 7.6 east plus 6.5 west. When we're adding those together, we can change the 6.5 west to negative 6.5 east, and 7.6 east minus 6.5 east is 1.1 east.